Hi guys, welcome to video lecture number 2, the life cycle of stars. In the last video, we looked at some of the categories or classifications of stars, and we described some of stars' basic characteristics like temperature and brightness. But a star's temperature, color, brightness are all determined by where it is in its life cycle, or what age the star is. By the end of this video, you should be able to describe the steps in a star's life cycle, including its formation, its expansion, and its death. And you should also be able to tell how a star's mass determines its life cycle, and relate that to other components of the universe like black holes, neutron stars, planetary nebula, and white dwarf stars. Go ahead and pause the video and record the essential question in your notes. In the last video, we talked briefly about star formation, but we didn't cover all of the bases. All stars are formed from nebula, giant clouds of dust and mostly hydrogen gas drifting in space. Not all nebula, however, are the same size. Some nebula are less than a light year across, and the largest nebula are hundreds of light years big. An average-sized nebula will form average-sized stars with average masses, just like our Sun. A really big nebula will form a really massive star, like Rigel, one of the stars in the constellation Orion. In either case, the stars are formed in the same manner. All that hydrogen gas from the nebula is pulled together by the force of gravity. When all that hydrogen is compressed into a very dense area, atoms begin bumping into each other, and all that friction creates huge amounts of heat. As gravity continues to pull atoms in the nebula together, the heat and pressure begin to make the hydrogen emit light. At this point, you have what is known as a protostar. A true star isn't formed until nuclear fusion begins in its core. So what is nuclear fusion? Remember in the last video I said that stars are the element factories of the universe. Nuclear fusion occurs when you squash two or more atoms of one element together to form one or more atoms of a new element, and it only happens under tremendous amounts of heat and pressure. In a star, the heat and pressure become so great that the hydrogen atoms in the star begin to get fused together to form helium atoms. This nuclear fusion releases huge amounts of energy in the form of heat and light. Stars are literally fueled by hydrogen and use it to create other elements. When an average star runs out of hydrogen to fuse, it begins to expand outward and becomes a red giant. This takes several billion years for smaller stars like the Sun because they fuse hydrogen more slowly than massive stars. Needless to say, red giant stars are very, very old. Because they no longer have hydrogen to fuse, red giants start to combine helium atoms to form other heavier elements, all the way up to carbon, element number 6. When a red giant star begins to fuse carbon, it's close to the end of its life cycle. There isn't enough heat or pressure to fuse carbon into something heavier, and there's too much pressure for gravity to hold the star together anymore. When an average star dies, it's a quiet death. Its outer layers drift back into space, creating a planetary nebula, with only its carbon-rich core remaining. The core is known as a white dwarf star. It's sort of like the skeletal remains of an average-sized star, and it burns very, very hot. Eventually, white dwarf stars will burn out and become cold chunks of carbon, but that takes so long that it hasn't happened yet. The universe is about 14 billion years old, which isn't enough time for a white dwarf to cool down. The life of a massive star down here is very different than that of a smaller star, and much, much shorter. A massive main sequence star burns much brighter and hotter than an average-sized main sequence star, and the hottest, brightest massive stars in the main sequence are known as blue giants. Rigel is a blue giant. Because they are much hotter at their core, stars like Rigel fuse hydrogen much faster than a smaller star, and they run out of fuel in millions of years instead of billions. It sounds all the same, but a million is a lot shorter than a billion years. When that happens, like their smaller siblings, they begin to expand outward and begin to fuse heavier elements. Because they're more massive, they expand further out than a smaller star, creating the class of stars known as red supergiants. Supergiants can fuse elements all the way up to iron before they die. And unlike smaller stars, they go out with a bang. When most of a supergiant's core is iron, it collapses on itself and creates a shock wave that forms a massive explosion called a supernova. A supernova is so bright, so powerful, that if a single star supernovas, the light that it emits outshines the light of the entire galaxy that that star is a part of. Think of that. One star among billions of stars outshining them as it dies. After the supernova, one of two things happens. The first possibility is that the core of the star collapses further, reducing all of the iron atoms into neutrons. A neutron star is about the size of the Earth, and it's a sphere of solid neutrons packed together with no space in between them. Since atoms are mostly empty space, the matter we interact with is almost all empty space. This makes neutron stars ultra-dense. A tablespoonful of a neutron star would weigh about as much as the entire Earth. If the star was supermassive, the second thing would occur, and I mean really huge. The material collapse wouldn't stop at a neutron star. The core of the star would collapse into the densest object in the universe, a black hole. Black holes are regions that have an inescapable pull of gravity. Not even light, which is the fastest moving thing in the universe, can escape them. At their center is the remnant of the largest stars, a singularity, a single point in space that has an almost infinite amount of mass. If you get too close to a black hole and cross what is known as the event horizon, there's no coming back. On that cheery note, thanks for watching. See you next time.